All right, so another related rates question. This came from our homework. This definitely by far had the most votes. So I'm going to go ahead and we're going to work through this. And at first, I'm going to read through this and kind of pull out the information that we need. Now, I do want us to keep in mind, we do have an acronym that helps push us through these questions. You know, I'm not a big fan of memorized processes, and this isn't really. It's just kind of splitting up a lot of the thinking that we have to do into kind of some stages. And it's not telling you exactly how to do it. So keep in mind our AL section of this is really to analyze the question and label the pertinent information. So it says a swimming pool is 12 meters long. Okay, so that's why they made it like this. That makes sense to me. 12 meters long. That was right there. Good. 6 meters wide. So it's really like, all right. So I almost kind of see that as like the front to back depth, you know. And then they say it's 1 meter deep at the shallow end. Okay, so I'm going to have to stop writing on this. And so that 1 meter deep at the shallow end, I really want to make sure I understand this. You see how this almost looks to me, if we look at it, it almost looks like a rectangular prism pool with a triangular prism deep end, right? So what they're saying is that this rectangular portion, right, is really 1 meter deep, right? And I'm going to go ahead and kind of erase that so you can see what I'm talking about. You can see where they label that 1 meter. And this is really why they had to give us an image because it's really hard to see it otherwise. So that 1 meter is there. All right. It says 3 meters at the deep end. Okay, that's why you have the 3 there. That already starts to make me think, right? Like if that, you kind of see how I saw it. See, there's this rectangular top part. That means that this bottom part is really 2 meters because that top part was really 1 meter. I don't know if that's going to become important. Maybe it will. Okay. It says water's being pumped in at a rate of 1/4 cubic meter per minute. All right, so they already labeled there. They already put that down for me. I just need to figure out what that is. Well, all right, isn't that just dVdt? It's how the volume is changing as time changes. So the rate of change of the volume with respect to time. All right, so that's meters cubed per minute. That makes sense. So we're pumping in some water. And it says there is 1 meter of water in the deep end. Water. And there is 1 meter of water. Okay, so that's, there's currently 1 meter of water in the deep end. There's not always 1 meter of water in the deep end. Because the water level is going to rise, right? Like, it's not all the time that there's 1 meter. So what I want to understand is right now, that's 1 meter of water in the deep end. But it's not going to stay that way. So that's definitely changing, and I want to understand that. Matter of fact, since that's changing, I'm just going to go ahead and say this is the depth of the water. And so, right, I know like I'm going to end up looking at like, when the depth is 1. That's like currently, but it's changing. I'm just going to write that down as a note. All right. Now I'm going to skip part A, because we don't need to do that. It's just a geometry problem, although they are trying to help you here. But it says, at what rate is the water level rising? So if the water level is rising, think about what's changing. That means that it's going to come up here, and it's going to come up here, right? So really what's changing is, the depth, right? So what we're really looking is for dt, the rate of change of the depth. And I'm really looking when d equals 1, and so we can see why I thought about that as currently, because that's when I want to evaluate it. It's not fixed at 1 all the time. It's only 1 when I want to find that value. Okay. Woo, that's a lot. So I have some information about the volume. I got some information about the depth, and I'm looking for other information about the depth. Now, feels like I pulled everything out of here, right? So what I'm on to now is this relating equation piece of our... I'm on to this relating equation piece. So I need to find a connection between volume and depth. And so if I just look at the water that's there, let's just look at that for now. What I notice, is it looks something, shoot, look at that. Isn't that like a prism? It's just on its lateral face. So I mean, like if you set it down, wouldn't it kind of look, and this isn't going to be perfect, but if I kind of stood it up on that, and I need to dot that because otherwise it's not a good picture, right? But if I stood it up, wouldn't it kind of look something like that? So I can see that this is a triangular prism, right? And so I dig back into my recesses of my memory, or just realize that all prisms are really just a whole bunch of stacked slices, right? Like I've got a slice here, and then I've got a slice here. I've got a slice here, right? They're just slices stacked on top of each other. So what I'm doing here by thinking about it as slices is I'm trying to help you dig back in the recesses of your memory to make sense of why the volume formula is what it is. But I'm also foreshadowing to what we're going to get into of calculus, is that really paper thin slices can be stacked on top of each other to create something that truly has volume. And we've talked about that briefly. But if I dig back, I know that volume of any prism is really the area of the base multiplied by the height. And there, my big B is area of the base. So if I look at this, my base is really a triangle. And if I come over in here, my base is actually that triangle right there, which isn't just any kind of triangle. It's a right triangle. And so in this case, I know that, that's going to be tough. What's that? So I know that this is my depth of my water, and I should have had that labeled still. But I also know that this is some length that I just don't know. But either way, I mean, if I bring that stuff out, my area, my base is going to be 1/2 my depth times my length, right? Because it's a triangle, 1/2 base times height. And this is, we can look at those two different things. And then what's the height of this prism? Well, if you come over here and look at it, that's the height of my prism, right? But when it's laying down, that height is here. It's here. It's really here. It's 6, right? So that's constant. That's never changing. That's always 6. And so I now have this volume equation. Now, this is great, right? I at least have some kind of relating equation. But ultimately, if I look at this equation, I'm not super satisfied because I do have V in there, which is awesome. And I do have D in there, which is what I'm trying to explore. But it's also got this other variable, L. And I know nothing about L. Matter of fact, I'm really annoyed, right, that L is in there. I wish L wasn't there. I wish it wasn't there. Which means this is the problem that I need to take care of. I am solidly still here in the relating equation piece, and I'm now going to have to kind of do a sub-problem. So I need to figure out something. Now, I want you to go back. In the video, remember I said we could look at this whole triangle right here, right? Because we said there's a rectangular prism sitting on top of a triangular prism. Now, if you look at that whole triangular prism bottom, and I just look at the triangle, and then I look at my current water level, which I'll go back to the green because I already have that on there, right? Right, it kind of looks like, it kind of looks like that, right? I mean, you can even see that in the big picture over there if I take out that little top part, right? You can see, and what do you notice? Well, to me, that really looks like similar triangles, They're the same shape, they're just different size. The pool, the water is slowly filling up this orange triangle, but that means the water, which I have drawn in green, is taking the shape of the larger triangle, right? So it has the same shape as that triangle. So let's see what we know. Well, I know this is D, and I've called this L, which is, that's fine. I should be using the same color green, but I'm not. And then remember earlier I'd said, well, okay, the whole depth is 3, but the shallow depth is 1, which means that just the triangular depth is 2. And then if we look even further, look right there, that 12, notice it's completely horizontal. That's really telling us that length right there, which isn't that the same as that length right there if I just transpose it down, right? So that's really 12. So keep in mind, I'm trying to find a relationship for L because I don't really want L. And what I found is that I have these two similar triangles, so I can set up a proportion. I can say 2 over 12 equals D over L, or in other words, 1/6 equals D over L, or in other words, well, if I solve that, I know that L is really 6D, right? If I just kind of rearrange that equation. And this makes sense because the length is huge and the depth really isn't. So I can just double check my formula. So with these, I now have some relationship for L, which means I can get that L out of there. So let's go ahead and do that. I'll switch back to my good color green. We had the volume equals 1/2 D times 6D, because that's my L, times 6, because that was this depth, right? Okay, so that really means that the volume, if I kind of rearrange everything, is 18D squared, right? Okay. Do I have a relating equation yet? Absolutely. I'm relating my volume and my depth, the things that I'm interested in. So now I can move on and take the derivative. If I take the derivative of this, I'm really trying to figure out how are these things changing as time changes. So I'm going to monitor that. So I'm going to get dv dt, which is great, equals 36 d, because I've got to keep in mind I'm chain ruling here, right? Chain rule, right? You can see it. And then times dd dt, the thing I'm interested in. So now if you look, it's just really just a matter of plugging in what we know. I know that 1/4, because that's dv dt, equals 36 times d, which the moment I'm interested in, right, we're moving on to this evaluate stage, so I can use that freeze frame, is 1 multiplied by dd dt. Or if we then solve this, and I'm going to come over here and clear out some space, if we then solve this, we're going to get, we can divide both sides by 36. Let's see, that's 120, that's 144. So I'm going to get dd dt is 1 over 144, because I've divided both sides by 36. And now I need units, right? So, and this is why I love this notation, right? dd. So how is d changing? Well, what are the units of d? Meters. And then how is t changing? Well, what is t? If I come over here, they were talking about t as being time in minutes. So I know it's changing at 1/144th, stress that to 100 or 144th meter per minute. So if I come in down and I would just write my final statement, the depth of the deep end is changing at a rate of 1/144th, which I just lost the screen, so I need to write a little smaller, 1 out of 144 meters per minute when the depth is, right, and I want to say the moment that I was actually interested in, when the depth is, 1 meter, right? And there we have our final answer. Now, I get why this question was probably a little more confusing for a lot of us. Some of us aren't ripping that structure apart. Some of us are not as comfortable with our geometry as we need to be. And then also we still had to find that similar triangle piece, right? which is, I mean, that's, I get it. So this problem is a little bit more involved, but it's a great example for us to look at.